PhotoScore LINCam is a position-sensitive, time-resolved, single-photon counting camera system. Here, I would like to explain how the camera works and what makes it so special. LINCam looks like an ordinary camera with a C-mount to attach it to an optical system. From my experience, when I say camera, everyone immediately has this in mind: the CCD chip, the matrix of light-sensitive pixels. To use this chip, you expose it to light. Then you read the data out, and what most people are interested in is how many pixels we have here and how many frames per second I can get. With the LINCam, it's different. We don't even have the concept of a pixel. We have no frames, but this is a camera. To understand how this is possible, let's take a closer look at a single pixel of a CCD camera. What happens here is the following. We expose it to light for some time to get enough photoelectrons. Then we need to amplify the signal and feed it into an ADC to get the code. That code is believed to be related to the number of photons that hit the pixel. In photon counting, we need some kind of light amplifying element that for a single incident, a photon will generate lots of electrons. Then we can further amplify, discriminate, and as a result, we know exactly the moment when it happened. By counting, we measure time. In this photo, you see the heart of the LINCam. This is a photomultiplier tube based on microchannel plates, or MCP-PMT. This is a vacuum-sealed ceramic assembly holding three key elements: a photocathode, a microchannel plate, and the anode. How does it work? Incident photon hits out a photoelectron that is driven by the electric field to the microchannel plate, which acts as an amplifier. The resulting electron avalanche is collected by the anode. Let's take a closer look at what's going on inside the MCP. In this cartoon, you can see the amplification process of a single charge carrier by the channel of the MCP. Commercially available plates gain up to 10 to the power of 4 electrons for a single initial photoelectron. Typical channel diameter is about 10 microns. Due to various reasons, we use an assembly of 2 MCPs that can gain us tens of millions of electrons. This amount of charge is something that we can start working with. This is a photo of an actual plate we use in LINCam. Before spats came around, people used such tubes to do time-resolved single photon counting. For that, you just collect the avalanche coming out of the MCP stack and get pretty good timing right out of the box. However, what we would like to do is get both time and position for every photon simultaneously. On the bottom left, you can see a rather simple position-sensitive anode. The blue area is the footprint of the electron avalanche emitted by the plates. The quadrant anode consists of 4 electrically isolated electrodes. Measuring parts Q1 to Q4, we reconstructed the center of mass of the electron avalanche footprint. An idea behind those formulas is rather simple. To calculate X position, you take the charge that falls to the right of the line of origin, Q1 and Q4, subtract the amount to the left, Q2 and Q3, and relate it to the total charge. This directly gives the position of the center of mass in coordinates that vary between -1 and +1. We can do the same with upper and lower charges to get vertical position Y. To grant roughly a megapixel resolution, we use hundreds of electrodes. So in reality, it's a bit more complex than what you see here, but the idea is the same. Inside the electronic module, we have 2 electronic processing pipelines running in parallel. For the time channel, we start with a high-frequency amplifier, feed it into a discriminator, and if we have a time reference signal, such as a pulse laser, we can measure time with picosecond range accuracy. For that, we use a time amplitude converter, TAC, coupled with an analog to digital converter, ADC. The charge acquisition pipeline starts with a charge-sensitive amplifier. This essentially acts as a pump for electrons residing in the anode parts. Then we have analog filters, and finally we feed the signal to the ADC in order to get the code for positional evaluation. So how does this allow us to get images whilst having no pixels? When we get a click, what we do is we add such a single line into a table. As data fields, we have X and Y positions. We have picosecond timing, delta t, and the absolute arrival time of the photon. With the next photon, we just append another entry, and another, and another. So a typical experiment results in such a table with 10 to 100 million of such rows. So as you can see, instead of pixels, we have positions here. We have no frames because the frames are just a range of rows in such a table. And nowadays, we have computers that are very, very good at querying the data. For example, you can make pixels of any shape. They don't need to be square. We can select whatever photon attributes to define the frame. But how do we get an image? For this, we just bin the photon positions into two-dimensional histograms, because the intensity is nothing more than a number of photons in that pixel. What happens here is the following. First, we define the pixels by the software. Second, we select a subset of photons to define a frame, and we build a histogram. At the same time, we build a list-like structure related to each positional bin. Thus, we can correlate, for example, timing with any set of markers of the original photons. To conclude, yes, this is a camera without any pixels. We store the attributes of single photons in lists. We use computers to access the data. Thus, we have full freedom in defining pixels or frames in the software. How can we use it? Let's take a look at the applications. Well, some of them. FLIM, Fluorescence Lifetime Imaging Microscopy. With LINCam, we can use virtually any fluorescence microscope. What we do is exchange a continuous light source for something pulsed, like a laser. Then what happens? We send an ultra-short light pulse into the sample. The sample gets excited, and after some time, we get a fluorescent photon back. Only a fraction of the excitation pulses result in fluorescent photon, so we repeat this process many times until we acquire enough photons to extract the lifetimes. This is a basic principle of measuring fluorescence lifetime by photon counting. Here we built a timing histogram for all the photons we acquired wherever they came globally, and we use statistics to resolve the individual components. However, we know the positions of the photons, thus we can retrospectively do a local mixture resolving of molecular composition. This is basically an idea of global analysis. One of the most exciting applications is the use of FLIM to measure fluorescence resonance energy transfer, or FRET. This allows us to measure intramolecular distances with angstrom accuracy using simple light microscopy. Here you can see an LCK molecule marked with two fluorescent proteins, CFP acting as a donor and YFP acting as an acceptor. In a non-stimulated state, the molecule is folded. We excite the ECFP chromophore, and this will very likely result in a FRET reaction, and we can see the light from YFP. Upon the activation, the molecule changes its conformation, and thus the FRET signal vanishes. Here you can see a human immune cell with an antigen-presenting cell that activates LCK. This starts a number of signaling cascades in our bodies as a reaction to inflammation. This has been a question for 30 years. How long does it take the immune system to start this response? The answer is 20 minutes. For more details, please see the publication. Another application we would like to show is metal-induced energy transfer, or MEIT. Here we have a fluorescent sample with some chromophores inside. If we cover the glass surface with a thin layer of metal, we can exploit timing to perform axial super resolution. Here the lifetime of chromophores is reduced because of the quenching in a similar way to FRET, but instead of acceptor molecules, the energy is transferred to the electron plasm formed by the film. On the figures you can see 3 human lymphocytes attached to the surface. Here LCK molecules located on the cell membrane are marked by GFP. It is important to mention that we can use total internal reflection fluorescence microscopy, or TIRF, because LINCam is a camera. The depth of the mite effect perfectly matches to a few hundred nanometers of the TIRF excitation depth. This is an intensity-weighted mean lifetime image. Here we performed maximum entropy-like analysis, defining the edges between slow and fast lifetimes that correspond to more or less quenched molecules. We can do mixture resolving of the molecules that are close to the gold surface and those that are distant. Thus we trade timing resolution for axial positional super resolution. This is another example of a mite sample, cells with labelled actin filaments. The decays corresponding to coloured regions of interest are shown below. As you can see, regions 3 and 4 are closer to the surface and consequently have shorter lifetimes compared to regions 1 and 2. Another fascinating application is time-resolved Raman spectroscopy. On this photo you can see a slice of stone covered in cyanobacteria. These black areas are photosynthetic cyanobacteria brought from Antarctica. Using a narrow slit, we directed the light into a spectrometer. Thus, we get a position and corresponding wavelength spectra. Instead of a simple gating of early photons, here we can apply a multi-exponential deconvolution. The fastest component, where tau is 0, corresponds to a sub-picosecond photosynthetic complex's fluorescence and the Raman signal fingerprint area. Now we can see the bands much more clearly. To the left you can see what one gets with a conventional sensor. To the right you can see significant signal-to-noise ratio gain. It is important to mention that this analysis really fits the fluorescence component rather than simply gating the early photons. Having a photon counting camera pushed us to test with more wide-field microscopy techniques. TIRF was already mentioned. Here we present a light sheet method. In the photo, you can see a commercial light sheet microscope. Luckily, it's equipped with a supercontinuum laser that gives full flexibility of wavelength selection. And it's pulsed. We performed a measurement of double transfected Drosophila larvae, producing a total of 128 sections. In these movies, you can see a 3D reconstruction of film image stacks. Additionally, we tested the Lightsheet Leica platform and the open source microscope setup, OpenSpin. One problem that many people face doing NADH imaging is the stability of the sample. Another problem is the extreme complex dynamics of NADH. I believe we can address both of those problems. Here you can see an image of yeast cell colonies with maximum entropy analysis. The analysis reveals 4 species of molecules: free NADH, NADH dimers, protein-bound and immobilized molecules. Here you can see continuous metabolic image recordings for more than 4 hours without any bleaching. The left movie shows metabolic waves of yeast cell colonies. The right is a Flynn and intensity video of lymphocytes acquired continuously with a pulsed UV excitation source for more than 4 hours without any bleaching. One of the latest applications of the LINCam is single molecule imaging. First in this work, 3 individual species were measured: Psi5, Auto 655 and Auto 647N. Then they measured a sample of the mixture of all 3 dyes. As you might know, The auto dyes used here are really close spectrally, but are easily resolvable on the basis of their lifetimes. This work was recently published, and the authors found a boost of 2 to 3 orders of magnitude in the acquisition performance. We look forward to seeing you on www.photoscore.de or write us a line to email@photoscore.de. Thank you.